All right, welcome back, scholars, to our third installment in our journey through sketching polynomials. Thus far, we've kept it nice and light. We're still kind of, feeling our way through and around, recalling some prior knowledge surrounding factors and using the zero product property to help identify those factors and how they pertain to graphical representation. We're going to start to kick things up and work interchangeably between polynomials written in standard and factored form, so we can describe features of graphs and expressions using precise language. I'll know I've got it when I can identify features of polynomials and their graphs using their standard and factored forms. All right, so in this case, I'd like for you to determine which one of the following expressions does not belong. Whatever response you feel does not belong, just make sure you provide some sufficient mathematical evidence to support your claim. All right, here, we're going to kind of get us started. We have a box with an algebraic expression that represents the volume of that box. I'd like for you to identify the degree and the leading term of the polynomial. I want you to explore here. I'm going to show you later on in this video, I guess, the proper mathematical step. So I wouldn't say there's necessarily like a formula to solve this, but I want you to explore here, right? How can you identify the degree? How can you possibly identify the leading term? Share that information with the class. And then without graphing, based on the information that you have here, what are the horizontal intercepts? What are the vertical intercepts? And based on this context, do those values make sense? Okay. This is kind of reinforcing this idea of inputs, outputs, domain, range, what's allowable, what's not allowable. And you'll be able to share it with your classmates and generate some type of dialogue before we get to class time. So as we've seen before, polynomials can curve up and down multiple times and have points that are higher or lower than the rest of the points around them. We call these points relative minimums and relative maximums. Sometimes if you're looking on other resources on the internet, you'll read the word local. Using the description in the following slides, construct equations for polynomial functions whose graph has the characteristics listed when plotted on the coordinate plane. That's awkward because that shouldn't be there. That was a bug. All right, so based in that volume question, to determine the degree, you might be able to use your intuition, but we must rewrite that polynomial from factored to standard form. I'm not necessarily sure how your previous teacher might have demonstrated or modeled that process, but with me, I like to use this idea of the area model. So when we calculate the area, we're taking the length of a rectangle and multiplying it by the width. In this case, we represent both the length and width with different algebraic expressions. The length is represented by the trinomial x squared plus 10x plus 7, and the width represented by the binomial 2x minus 1. The area model, then, we can subdivide each term and break the rectangle into smaller components that we sum at the conclusion to calculate the area of our algebraic rectangle. X squared times 2x, right? Because we have this column times this row, give us 2x to the third power. Replicating that process, we have 2x, because we're in the first row, times the second column of 10x, 20x to the second. And the final column times the first row would be 14x. Fast forwarding that process, here are our remaining pieces. Now you'll notice that we have the 2x cubed and the minus 7 as prefaced here in the standard form of the polynomial. To acquire the 19, if we combine negative x squared plus 20x squared, that would yield a positive 19x squared. And if we combined negative 10x with 14x, that would yield a 4x. Both have pros and both have cons when it comes to sketching polynomials. I'm not going to specifically state what those are because I would like for you to start to consider what are the strengths of each form, what are the cons of each form, so we can obtain a better grasp. So I've used some vocab previously in this video that should allow you to compare and contrast these two function representations that you have here for m and k. I also provided a graphical representation so you can discuss both the algebraic similarities and differences as well as the graphical similarities and differences. We have this function here, p of x, and it's given by x plus 1 times x minus 2 times x plus 15. Mine concludes that the graph looks like a parabola, so it must be a quadratic. Do you agree? Yes or no? I'm going to leave it at that. But I will tell you to make sure you attend to precision here. Don't judge a book by its cover. In the previous screen, the viewing window spans the points from -10 to 10 on the x-axis and -40 to 40 on the y-axis. How can we possibly modify that window before graphing an expression like p of x so we can see the main features of the graph? So what that basically means is if you said, yes, it's a quadratic, you, my friend, are incorrect because there are 3 factors here, thus making it at the very least a third degree polynomial. Okay. So how can we modify that viewing window so that way we can possibly see the x-intercept that is missing? Because I can see that we have the x-intercept at 2 and the x-intercept at -1, but we are missing an additional component. So how can we modify those viewing bounds to allow us to see the complete picture? After we arrive at that, right, what viewing window would we choose for graphing this polynomial? Right, currently it's in factored form. As I mentioned previously, there are pros and cons. One of the big cons to factored form is it does not really take into effect the behavior of the function over larger values, right? So something to take into consideration when you're trying to determine what viewing window you would choose for graphing. Oops, we don't want that there. No, don't flip me. Now I've gone away. Where's my screen? I hope my face is still there. Hope you can hear my voice. Anyway, so write a plausible equation for a polynomial whose graphs have the following horizontal intercepts. As you saw before, that expression can be represented by x minus 4. I could have also done, if I wanted to, negative x minus 4. Oops, sorry, brain fart. I could have made my expression this as well. I could have modified the equation accordingly. It worked. Let me see, x minus 4. Nope, that should be 16. Right. So there are infinite, in theory, amount of responses that could necessarily apply. So as you're going to make your way over the next couple of slides, where we give you various different horizontal intercepts to intersect, you can write your expressions in factored form or standard form. And once again, I'm going to continue to reiterate that there are pros and cons to both formats. In this case, you might preference one format over the other. I totally would, but I want you to establish a sense of familiarity with your own constructions.